Welcome to the third lecture in the unit on causal inference. In the previous lecture, we talked about randomized experiments, and today we're going to do a whirlwind tour of observational studies. Okay, so here's the overview for today. So first, we're going to ask why observational studies? Why can't we just stick with experiments? And then and after we convince ourselves that this is what we want to do, we have to ask what can go wrong. So once we don't have randomization, so once we do observation studies, we lose randomization or randomized treatment. So what can go wrong in that case? And now we want to overcome this, and the way we overcome this is using this assumption called the unconfoundedness assumption. Okay, so we're going to introduce what this is and what it means. And then we're going to talk about three different methods of estimating the ATE. Okay, so this is outcome regression, inverse propensity score weighting, and matching. Okay, so we sort of don't really have time to talk about matching, so we're going to focus on the first two. So why do we want to move away from randomized experiments? Okay, so here are a few reasons. So first, the experiments that we conduct may have low power. Power refers to our ability to detect significance or signal wherever when it exists in the data. And if we do experiments, we just may have low power because of small sample sizes. Okay, so when sample sizes is small, then all the p-values that you get are going to be larger in some sense because you just have few samples to detect significance in the data. Okay, and the reason why sample sizes are usually small in experiments is because experiments are just expensive to run, and for every additional unit that you enroll into your experiment, it usually is going to cost some amount of money or resources, and you want to minimize this. Okay, so for instance, for drug trials, every patient that you enroll into the trial has to receive medication. Medication might be expensive, and they have to undergo follow-up. So they have to keep coming back to the hospital or whatever center, and all of this is going to cost thousands and thousands of dollars. Okay, and apart from the experiments that we can actually run, but cannot have too big sample sizes, some of the experiments are just infeasible. Okay, so it might be just too expensive to conduct the experiments at all. Okay, and more than that, some experiments are just unethical. So we just are not able to run them, even if we had all the resources. Okay, for instance, smoking and lung cancer. Okay, so why has there never been an experiment to test this? It's because of ethical reasons. We just cannot randomize people to smoke or to not smoke, right? Because we already have a significant belief that smoking poses quite a severe health risk. Okay, and so whenever we are faced with these situations, the only hope that we can have is to work with observational data. But the good news is that there's often a lot of observational data. Okay, observational just means non-experimental, anything that does not come from an experiment. Okay, so here are some examples of types of observational data. Okay, so this credit card transaction information, websites, user logs, electronic health records. So this is a big one that's becoming very popular nowadays. Census records, tax returns, satellite images, and etc. Okay, so in the era of big data, we have more and more data from many different sources, and it's very tempting to ask, can we use all of this data to do causal inference? Okay, in some cases, the answer is yes, with some caveats. Okay, so this is what we're going to discuss in the rest of today's lecture. In this video, we are going to talk about what can go wrong when you try to do causal inference in an observation setting. So we usually work with a superpopulation when we deal with observational data. Okay, so this moves away a little from the fixed experiment population that we have for randomized experiments. And so we need to make the following adjustments. Okay, so the I is still going to be our treatment indicator. So this is going to be 1 if unit I is treated and 0 otherwise. yi0, yi1 are still going to be our potential outcomes. And now we're going to have a new character, xi, which is going to be a covariate vector of unit I, and you can think of this as measuring, for instance, the age, gender, or other features of a person. And now, the superpopulation assumption is that we assume that we observe IID samples comprising a tuple of all of these variables. So Ci, yi0, yi1, and xi that are drawn from a superpopulation. And this is another way of saying that these are drawn from some density over the variables z, y1, y0, and x. Okay, so you have some distribution, and we draw IID samples, and this is going to be what we observe in our observational setting. And so now the meaning of the ATE is slightly different. The ATE, which stands for the age-rich treatment effect, okay, so it's now going to be an expectation instead of a sum. Okay, so it's defined to be the expectation of the potential outcome on the treatment minus expectation of the potential outcome under control. Okay, so this is our model. And now what goes wrong? Okay, so what goes wrong is because we observe only not the expectation of the potential outcomes, but conditional expectations. Okay, so we observe the potential outcomes on the treatment for the group that was treated, and the potential outcomes under control for the group that did not receive treatment. Okay, and in general, these are different from the expectation of the two potential outcomes, respectively. Okay, and so the consequence of this is that the prima facie treatment effect, which is defined to be, okay, so this is denoted tau PF. This is defined to be the difference between these two means. Is not the same as our ATE tau. So how do we get around this? Well, we can actually just write out what tau is in terms of conditional expectations. Okay, and we do this by spanning the two expectations. Okay, so I'm going to write the first term as conditional expectation of y1 given z is equal to 1 times probability z is equal to 1 plus expectation of y1 conditioned on z is equal to 0 times probability that z is equal to 0. That's the first term. And similarly, we can expand the second term as the sum of two conditional expectations. Okay, and this should be a minus. And then I have to put a parenthesis around both of these terms. Whoops. Okay, so we can write tau this way. The problem is that the two terms over here that I'm highlighting are terms that we do not observe. So we do not observe the highlighted terms because these are the counterfactual terms. All right, because this is saying so that the term on the top over here is going to be the average of the outcome under treatment for the group that was not treated. Okay, so this is the other alternate universe that we don't get to see. And similarly, the term at the bottom is going to be the average outcome under control for the group that was treated. So we do not observe these terms. So we have, in general, we just have no hope for identifying tau. Okay, so tau is not identifiable unless we make some further assumptions. And we're going to see in a bit what assumptions we can make. But for now, let's return to randomized experiments. And let's see what randomization gives us. Okay. So by randomization, the treatment indicator becomes independent of the potential outcomes, y1 and y0. Okay. And just a remark that this is not saying that z is independent. And then maybe let me just use the symbol. Z is independent of the observed outcome. So long as the treatment has some kind of effect, then Z is definitely not independent of the observed outcome, but it is independent of the pair of potential outcomes because it only affects the outcome through which of the two potential outcomes you see. Okay, so in the randomized experiment setting, we had a fixed table, the science table of potential outcomes. So y1 and y0 are just numbers. And here we have a superpopulation. So we do assume that y1 and y0 are being drawn from some distribution. A randomization means that z, the treatment indicator, is independent of these two. Okay, so the only dependence of the outcome on z is which word you actually get to observe. Right, and now we can sort of see how this allows us to to actually observe and identify the treatment effect. Okay, so based on this independence assumption, we have that. Okay, so this implies that the conditional expectation of y1 given z equal to 1 is going to be the same as the conditional expectation of y1 given z is equal to 0. All right, so this is the definition of conditional independence. And so, because the two conditional expectations are the same, the unconditional expectation is also going to be the same. Right, and analogously, the unconditional expectation of the potential outcome under control is also going to be the same as the conditional expectation. And what this implies is that the ATE is going to be equal to the prima facie treatment effect that we defined earlier. Okay, and this quantity on the right is what we actually do get to observe. Okay, so this is the value of randomization. It allows us to identify the treatment effect, whereas in the general case, we are not able to do so. Okay, so in the next video, we're going to consider a concrete example in order to illustrate what we just said. Let us now return to the kidney stones example that we used to illustrate Simpson's paradox. We're going to recast it in terms of an observational data causal inference analysis. Okay, so let's make some definitions. So a treatment indicator is going to be whether or not the patient underwent treatment B. Okay, so this is 1 if they took treatment B, and it's going to be 0 if they had treatment A. And then the potential outcomes are going to be whether or not the patient recovered under these two different treatments. And then we have a covariate variable, which is going to be whether or not the patient had small kidney stones. And now, what we observe in this table are going to is the rate of recovery, meaning how many patients, what proportion of patients recovered amongst those who took treatment A and amongst those who took treatment B. Okay, so it's going to be 83% and 78% respectively. Okay, so these can also be written in terms of conditional expectations. Okay, so this 83% is going to be the expected, the probability of recovery under treatment A for those patients who took treatment A. Okay, so we're conditioning on this subpopulation. And then there's 78% is going to be the probability of recovery under treatment B for the patients who took treatment B. And what we computed the last time was simply the prima facie causal effect under this setup. Okay, and we saw that it is minus 0.05, which in other words seems to suggest that treatment B is 5% more successful than 5% less successful than treatment A. Okay, and in Simpson's paradox, we talked about why this is not exactly fair. And here, when we try to cast this in terms of potential outcomes, we again see why this is not really a fair comparison. And that is because of selection bias, as we said in the previous video. Okay, so conditional expectation of the potential outcome given z is equal to 1 is not exactly the same as the unconditional expectation of this potential outcome. Okay, so this does not hold generally. And in our case, we have some evidence that to suggest why this also does not hold. Okay, and that's because we know that the treated groups and the control groups are different in terms of this covariate that we measure, W, whether or not the patient has small kidney stones, right? So amongst the patients who received treatment B, only 25% had small kidney stones. And amongst the patients who had treatment A, 77% of them had small kidney stones. So these two populations, the population over which Z is equal to 1 and the population over which Z is equal to 0, are very different populations, okay, which suggests that equality shouldn't hold in terms of the potential outcomes either. So far, we've been talking about what can go wrong in observational studies. Now let's try to find a way out. All right. And to find a way out, we need to, essentially, this means that we need to find a way to identify the ATE. So let me say a few words first about what identification means. Okay, so we say that some parameter data can be identified if there's a way in which we can know what it is if we have infinite data. So if we remove all sampling considerations and constraints, then we have a way of knowing what that parameter is. For instance, if you have an infinite number of RAD draws from some distributions, you can identify what the mean of that distribution is. Okay, and in the randomized experiment, we can identify the ATE, but once we drop that assumption, then as you saw in the previous videos, we can no longer identify the ATE. Okay, so let's see how we can get back what we want. So the assumption that we had in the randomized experiment that allowed us to identify the ATE was precisely this independence assumption between the potential outcomes and the treatment indicator. Okay, so this is sort of what you get when the treatment is randomized. Now, if you're not doing a randomized experiment, how do we get back this crucial assumption? One way is to pretend that we have some natural experiment in which nature is doing the randomization for us. Okay, so there may be a few examples where this might be true, but generally it's a very stringent assumption and this almost never holds. Nature is often not so kind to us. So we need to find another assumption or relax the assumption a little bit to something that is a lot more plausible in real life. Okay, and the change that we're going to make is to do conditioning. Okay, so we're going to condition on X and then make the same assumption. And this assumption is called the unconfoundedness assumption. Okay, so this is called unconfoundedness, and it has some other names as well. So this is also called ignorability or exchangeability. Okay, unfortunately, there are many names for this, but let's stick with unconfoundedness because I think it's a more informative name for this condition. Okay, so what is this saying? This is saying that essentially, once you condition on X, meaning that you only consider some strata on X, then within that strata, we are essentially running a randomized experiment. Okay, so all of this is very abstract. We're going to see some examples of this later on, of cases where it's reasonable to, it might seem reasonable to assume this, and other cases where it's probably not so reasonable. But for now, let's see what this gives us. Okay, so let's define tau x to be equal to, okay, so I want to make this a small x. So this is going to be the treatment effect within a strata of x, okay, and to keep everything simple, we can assume that x is a discrete random variable. Or maybe if you want, you can even be binary, as in the kidney stones example. Okay, and then, so this is what we want. What we do know is this prima facie causal effect, which is going to be this, but then with further conditioning on treatment. Okay, and this is what we actually observe. Okay, and now we see that if unconfoundedness holds, then okay, I'm just rewriting this, changing swapping the locations of z and x. Then because after condition x, the potential outcome is independent of my treatment, so I can drop the conditioning on the treatment. Okay, so this is what it means to be conditionally independent. And likewise for the potential outcome of y0, and hence, okay, so let me just pretend that I finished writing this out. Oh, I might as well just finish writing it. So hence, this implies that tau x is equal to tau prima facie x. Okay, and the whole point is that we actually tau the prima facie causal effect is exactly what we observe, and so now we can use what we observe to what we observe is the same as what we want. And then tau, okay, so now let's assume that if x is discrete, then tau, the ATE, okay, so this is just going to be the expectation of tau x, right? Okay, so maybe let's do this slowly, improve it. Okay, so first I use the tau property to say that this is equal to okay, so let's do it this way. Okay, so I'm using the tau property here. And now the quantity inside the first expectation is just tau of x. Okay, so I shouldn't put this. Okay, so now x is going to be the random variable. And now by definition, this is equal to the sum of tau little x times probability that x is equal to little x, where I sum up over all the x's. Okay. And from above, we can replace tau x with tau prima facie x, and the probability is still there. Okay, so then we can see that we know tau prima facie x because this is what we observe from the data, right? Okay, so both of these quantities are things that we actually observe. And we also observe this probability because this is because we are drawing IID samples with the x variables, so we just need the marginal of the x distribution. Okay, so we know this, and px is equal to x. So we can use this to identify tau. Okay, and this is what you do when you have infinitely many samples. And then when we have finitely many samples, we can use plug-in estimators for everything. All right, so then tau EF of x is equal to, okay, so previously used the conditional expectation. Now it's going to be a sum of, let's see, yi, observation, and we're summing over xi is equal to x, and the I is equal to 1. Okay, and then I'm going to divide by the size of this. Okay, so I'm just going to call this n1x, and minus 1 over n 0x summation xi is equal to x, ci is equal to 0, yi ops, where n1x is equal to number of units, so that xi is equal to x, ci is equal to 1. And n0x is defined analogously. Okay, so this is the plug-in estimator of that prima facie causal effect. And then plug-in estimator of this probability is just going to be 1 over n times the sum of indicators xi is equal to x. Okay, so it's a fraction of samples that has, for which xi is equal to level x. Okay, so then putting everything together, tau hat is going to be sum over all levels of tau prima facie x times this plug-in probability. Okay, so now we know how to estimate the ATE when we have this unconfounded assumption. But more than that, in this case, we are sort of having this, we're taking averages for each of the levels. And so this sort of relies on the fact that this relies on the assumption that x is discrete. And furthermore, if you want this to be efficient, then x needs to have very few levels. So we can do better. And in fact, we need something else whenever x is continuous. Okay, so when x is continuous, or when x has many levels, then we need some other methods. Okay, and we're going to talk about these in the future videos. So I'm just going to say what these methods are. Okay, so 3 broad classes of methods. Okay, so one is regression. The second is propensity score weighting. And the third is matching. Okay, so we're going to see these in future videos. We are now going to talk about the concepts that we covered in the previous video and the context of the kidney stones example. So here I've rewritten what we had on the slides previously to take a moment to refresh your memory of what all the definitions are. Okay, so now let's assume that unconfoundedness holds for the kidney stones example. And here unconfoundedness means that once we condition on the size of the kidney stones, then the choice of treatment between treatment A and treatment B is essentially random. Okay, so maybe you want to believe this assumption or not. Well, let's suppose it holds for now, and then we can go ahead and compute what this gives us. Okay, so this was the table that we saw. And so now we want to compute the ATE, or an estimate of the ATE. So we have to compute this conditional average treatment effect function, and we need to compute what the value is at 1 and at x is equal to 1 and when x is equal to 0. Okay, so let's write out the definition. Okay, so I'm just writing out the definition of what tau of 1 is. And now, based on the unconfoundedness assumption, okay, so this is by unconfoundedness. This is the same as this conditional expectation, but with an additional term in it. And likewise, the second term is equal to this conditional expectation with z is equal to 0 tacked on and the conditioning. Okay, so this is what unconfoundedness gives us, and this is what we want because now this is actually what we observe. Okay, so if we go back to the table, the first term on the left is going to be the probability of success of recovery under treatment B for those patients with okay, and all these small x's should be 1s. Okay, so the first term over here is going to be the probability of recovery for patients with small kidney stones and who received treatment B. Okay, and so this is going to be 0.93. And then the term on the right is going to be the probability of recovery under treatment A for patients with small kidney stones and for patients who received treatment A. Okay, so looking at the table, this is going to be 0.87. And so we get 0.06. And for tau 0, we compute it in a very similar way. Okay, so this is now going to be about the quantities and the middle row of this table. So this is going to, sorry, in top row of this table, so this is going to be 0.73 minus 0.69, which is going to give me 0.04. And now I can write that tau in terms of sorry. Okay, so I can write it in terms of this conditional expectation times probability that x is equal to 1 plus tau 0 times probability that x is equal to 0. And we know what these probabilities are. probability that x is equal to 1 is simply the proportion of patients with small kidney stones, which is 0.51. Okay, so we get 0.06 times 0.51 plus 0.04 times 0.49. And now we see that this is going to be approximately 0.05. Okay, so under the unconfidence assumption, we've formed an estimate for the ATE. Okay, and this is an ATE of choosing treatment B over treatment A. Okay, so here in the notation, I did not use the sample notations, but yeah, you should bear in mind that all of these are about samples. We now turn to methods for estimating the ATE under unconfoundedness. The first method is outcome regression, and the name of the method sort of implies already what it is about. Okay, so we want to fit a model for predicting the outcomes given the covariate vector x. All right, and so the starting point is recognizing that the ATE tau can be written as the expectation of the function tau of the variable x, or in other words, the integral of the function tau x times p of x dx, where p of x is going to be the density of x okay, and to remind you, this function tau of little x is equal to the conditional expectation of y1 condition on x being equal to small x minus the conditional expectation of y0, again conditioned on x being equal to small x. Okay, and let me introduce some terminology. So this is called the conditional average treatment effect function. Okay, and this is often contracted to the acronym KIT. Okay, so now what do we do? Okay, so given, so now, okay, so let me just say broadly what the two steps of outcome regression is. Okay, so outcome regression comprises two steps. Step one, estimate the KIT via some estimator tau. And then step two, we use the plugin estimator for the ATE tau. Okay, so i.e. we substitute the density P of x with the empirical distribution P hat of x. Okay, and this is the same P hat of x that we talked about in the bootstrap. Okay, so this is equal to a uniform distribution on x1 to xn, where these are the samples that we observe. Okay, so hence tau is going to be equal to the average over the xi's of tau hat applied to each of the xi's. Okay, so this is what outcome regression is. And the crux is really the first step. And the second step is something that you naturally do in many cases. Okay, so the tricky part is estimating the kth function. Okay, and that turns out to be pretty tricky. Okay, so we need to estimate. Okay, so to estimate tau is tricky. Okay, and it turns out that there are several strategies of doing so. Okay, so this is a topic of active research. So let me just tell you two broad strategies that people use to estimate tau hat. So many strategies. Okay, so we will state two. Here's a strategy one. Strategy one. Okay, so for the joint model for the function mu x comma z, which is defined to be conditional expectation of y given x is equal to small x, z is equal to z. Okay, so we're concatenating the covariate vector as well as the treatment variable. Okay, and then we observe that tau of x is equal to mu x comma 1 minus mu x comma 0. Okay, so if we estimate mu of x comma z, then we get an estimate for tau. Okay, so that's the first strategy. Strategy number two is to fit two models. Okay, one for the outcome under treatment. Okay, so this should be the potential outcome under treatment. Okay, but here we have already conditioned on the treatment group, so this is the same thing. Okay, so one for this. Okay. So perhaps it's clearer to write it this way, one each for this function and another for mu sub 0, which is conditional expectation of the outcome given x is equal to small x and z is equal to 0. And now we observe that tau x is equal to mu 1 of x minus mu 0 of x. Okay, so if we estimate these two outcome regression functions, then we also get an estimate for tau. All right, so what do we use to, so now what can we use to estimate mu 1, mu 0? So you can use any supervised learning algorithm that you've seen before. So you can do a linear model, you can do GLM, or we can use non-parametric methods or machine learning methods. Okay, but whatever you choose, there are going to be some problems. Okay, so for the first two, the model may be misspecified, which we talked about in the lesson for GLM. And so the model is misspecified, then you may not actually get the right answer for tau of x for the kth function. And so your estimate for the ATE may be wrong. And then for the ML method, so this is more flexible. It's non-parametric, so it's not going to be misspecified. But what happens is that there will be problems with overfitting. And also with extrapolation. Okay, so in the classic setting for ML, we don't really extrapolate, but in causal inference, because of the difference between the treatment population and the control population, we often have to extrapolate the model predictions to samples that are not so close to the samples that are used to train the model. Here's a fact that is nice to know, especially if you are into econometrics or other social sciences. Okay, and this is what happens when you use strategy 1 with a linear model. Okay, so recall that strategy 1 was fitting a joint model for the outcome y with respect to both x and z simultaneously. Okay, so i.e., we regress y against x plus z. And then what we get is a model y is equal to alpha hat plus beta hat transpose x plus gamma hat z plus epsilon. All right, and epsilon is defined as the remainder after fitting your regression. Okay, then if this is the case, the claim is that your estimate for the ATE is going to be the same as the coefficient for the treatment indicator. Okay, so here's a quick proof. So the proof is that, let's do a computation for what happens for the kth function. Okay, so because we're using the first strategy, this is going to be the difference between mu hat of x comma 1 minus mu hat of x comma 0. Okay, but from the regression, we know that mu hat of x comma z is equal to your these predictions alpha hat plus beta hat transpose x plus gamma hat z, okay, and no epsilon term. And so now when you take the difference between these two, alpha hats and the beta hat transpose x terms cancel, and we just get gamma. Okay, so now when you take an average over the kit, then we get that tau hat is equal to gamma as well. Okay, so this proves the fact. And now we see why in econometrics is often what often happens is that people usually take the coefficient of the treatment as of some variable as a measure of the strength of its causal effect. Okay, so this sort of justifies what they are doing, but also now we know that this relies on this linear model assumption. Okay, so it relies on assuming that the true relationship between y and x and z is linear, right? So that when we fit this linear model, we actually get something that is a good estimate, a good fit to the true kit function or the true outcome function. And if that's not the case, if the model is misspecified, then we're going to end up with something else. Okay, and this is, in that case, taking the coefficient of your treatment as an estimate for its treatment effect is probably not the right thing to do. The next tool in our arsenal for estimating the ATE is inverse propensity score weighting. Okay, so I have to define for you what propensity scores are. But first, let me show you this diagram that gives you another way to think about observational studies. Okay, so when you only have observational data, your population of interest is going to consist of some mix of treated units and untreated units. All right. And so when we simply look at what happens in the treated group and what happens in the control group, then this is only going to give us association, right? Association means that you can compute these conditional expectations, but they do not give you the unconditional potential outcome averages. And what we really want to do is to look at the difference between these two unconditional averages. Okay, so the notation here is a bit different because I took this from the textbook. There's different notation. So here we have to use Z instead of A, and instead of using the superscript, this means what the potential outcome Y of 1 and the potential outcome Y of 0. Okay, but in this diagram is a nice illustration of what's the difference between causation and association. And it also gives you a hint for what you can do in order to estimate ATE once you assume unconfoundedness. What you want to do is to construct a pseudo population. Okay, so this is the population you observe, but you want to construct two pseudo populations. A pseudo population in which every single person received treatment, and a pseudo population in which every single person did not receive treatment. Okay, and the way we do this is to do some weighting based on the covariate distribution that is in treated group and the covariate distribution that we have in the control group. Okay, and this is the essence of propensity score weighting. Okay, so now the central character of the story. Okay, so this is the propensity score. It's often denoted E of X. Sometimes it's also denoted pi of X, but I think E of X is more common. And this is simply the probability of being treated conditioned on your covariates being equal to some level of X. Okay? And so if X is continuous, this is going to be a function of a continuous variable. And okay, so you can think of this. So when we fit the model for the propensity score, you can think of this as solving a classification problem where we're trying to predict whether or not some patient was treated. Okay, so now we know what propensity scores are. Now let's see how we can use them. Okay, and here I'm drawing you a tree diagram that will help us along our way. And this tree diagram is a way of thinking about how to divide up our population into different subgroups, depending on first what the observed covariate is, whether X. So here I'm using binary covariate for simplicity. So whether X is equal to 0, X is equal to 1, and then we further subdivide each of these subgroups according to whether they're treated or not. And then finally, for the observed outcome, so let's assume the outcome is binary, whether or not the outcome is 0 or whether the outcome is 1. Okay, so we have 3 different binary variables, which gives us 8, 2 to the 3, which is 8 different strata in total. Okay, so this is a tree diagram that illustrates what happens to your study population. Okay, so now let's give some further meaning to it. So let's apply this to our kidney stones example. Okay, and everything fits very nicely. So recall the X covariate was simply whether you had small kidney stones or large kidney stones. Okay, so we use X is equal to 1 to denote small kidney stones. So X is equal to 0 indicates large kidney stones. And then Z was whether or not So Z equal to 1 means they received treatment B, which was the more aggressive treatment. And Z is equal to 0 is treatment A, which was the less aggressive treatment. Y is equal to 0 means that the procedure failed. Y is equal to 1 means their procedure succeeded and they recovered. Okay, so that's the interpretation in this example. And the numbers in red denote the respective probabilities. Okay, so 51% of the patients had small kidney stones. And then, okay, so let's look at the large kidney stones patients first. Okay, so I just filled in all these numbers from the table that we saw earlier in these slides. So all the patients with large kidney stones, 23% of them were had treatment A, 77% of them had treatment B. And then all of the patients that had treatment A, 31% of them did not recover, 69% of them recovered. Okay, and the other numbers here are defined analogously. Okay, so I just want to say that that these are not the exact numbers, so we did some rounding. Okay, and the rounding is going to come back to bite us a bit later, but for clarity, I have to round the numbers here. Okay, so just a note. So what is the meaning of these numbers for Z? Okay, so this 0.24 is simply the proportion of units who had large kidney stones who received treatment, and then simply the propensity score. Okay. Okay, so there's a mistake here. So this should be E of 1, and this should be a 1. Okay, so this is the propensity score for X is equal to 1. Okay, it's the probability of being treated. Okay, and likewise, this over here is going to be 1 minus the propensity score at 1. Then this is going to be the propensity score at 0, and this is 1 minus the propensity score at 0. Okay, so the numbers in the second column have the meaning of propensity scores. Okay, and now let's see. Okay, so now I'm writing in the last column here, I'm writing down the number of patients that were in each of these strata. Okay, so I just obtain all of these numbers from the table. And I'm drawing this diagram here that there's a the symbol here which comes from the diagram that started off this video. Okay, because this is the mixed population. So this is the mixed population that we actually observe. Okay, and now from this, we want to construct our pseudo-populations. Okay, so the first pseudo-population. Okay, the pseudo-population that will exist in ward A, in which everyone got treated. So what do? So first, we pretend that everybody was sorry, this is the ward in which everyone did not receive treatment A. So they're in the control group for this example. Okay, so we pretend that everybody received treatment A. So we cross out this probability and we change it to 1. We cross out this one and change it to 0. Okay, and likewise for the other strata. And now, if that's the case, what do? Okay, so now I'm enlarging the size of the strata by a factor of 1 over 0.23. Okay, so it's 1 over the propensity score. And so if I want to know in that population how many people had a negative outcome and how many people had a positive outcome, I should simply just reweight or multiply the original number of patients in that strata by the factor in which we enlarge this population. Okay, so I have to multiply this by 1 over the propensity score. Okay, so let me repeat. So we're enlarging this group of patients, the strata for, so first we're looking at the patients with large kidney stones, and then we're enlarging the strata of patients who received treatment A by a factor of 1 over 0.23. We're pretending that everybody received treatment A. And so because we're enlarging the strata by that amount, we have to enlarge the number of patients who had a negative outcome or who had a positive outcome by the same factor. Okay, and then we get these numbers. And then analogously, we can do the same thing for the patients who had small kidney stones, except that the propensity scores are different. Okay, so this time it is 0.24 and not 0.2, instead of 0.24 and not 0.77. So now I have to multiply this by 1 over the other propensity score instead. And okay, and I also misspoke. Okay, so this is 1 over 1 minus the propensity score. Okay, so this is 1 over 1 minus E of 1, and this is 1 over 1 minus E of 0. Okay. And now, after I get all these numbers of patients, I can compute the average outcome. Okay, so for the average outcome, I multiply Y times the number of patients in that strata plus 0 times the number of patients in this strata. And then the same here, 1 times the number of patients in this strata plus 0 times the number of patients in that strata. But then all the strata with 0 don't actually count, so I just need to sum up these two. And I now divide it by the total number of patients in the entire study, which is 700, and I get 0.781. Okay, and now I can do the same thing by pretending that all the patients received treatment B. Okay, and so now I actually do multiply by 1 over the propensity score, and I get these numbers. Okay, and then I can compute the average outcome in the same way, and I get 0.838. So now I know what happens in ward A, where everybody received treatment A, and now I also know what happens in ward B, in which everyone received treatment B. And so to compute an estimate for the ATE, what I do is that I take the difference between these two averages. Okay, so difference is 0.838 minus 0.781, and we get 0.057. Okay, so this should actually be the same as the answer that we got previously. So we already had an estimate for the ATE by computing just the averages in a different way, and it should actually be exactly the same. Okay, so I remember that I wrote down it was 0.05, and the reason why the two numbers are different was because of rounding. Okay, so there's rounding here, and we also did some rounding in the previous calculation. Okay, but if you did everything exactly, the two numbers should be exactly the same. We can now formalize what we did in the previous video and write a theorem that applies to propensity scores. So here's the propensity score theorem. Okay, so let's assume unconfoundedness, which is that the potential outcomes are independent of treatment given the observed variable x. Then first, if we consider the outcome, the observed outcome y times, okay, so to be pedantic, I'm going to write in the subscript times the treatment indicator z, and we divide this by the propensity score, and we take an expectation, and this is equal to the expectation of the potential outcome on the treatment. Okay, and so this says that if we reweight all of our samples by the propensity score in order to construct our pseudo population, and now we average the outcomes over the pseudo population, then this is the same as taking an average over all the potential outcomes for under treatment. Okay, and likewise, if we multiply the observed outcome by the indicator of the control group, which is 1 minus the treatment indicator, and divide this by 1 minus the propensity score, take an expectation, and this is going to be the unconditional expectation of the potential outcome under control. And now we can put these two together to get a hold of the ATE. Okay, so this is going to be simply the difference between these two terms. Okay, so maybe I should have just copied and pasted, but that's all right. I've already written this out. And so now this allows us to identify the ATE. Okay, so this is the second way we've seen of identifying the ATE, and it lends itself to an estimator. Okay, so for finite samples, we have the inverse propensity score weighting. Okay, so this weighting scheme is called the inverse propensity score weighting. Inverse propensity weighting. Okay, and this is denoted IPW for short. Okay, so in causal inference, there are a lot of acronyms, so you just have to get used to it. Okay, and this is denoted tau sub IPW. And here, we're just going to take an average over all of our samples of yi times zi over e of xi minus 1 over n sum from 1 to n yi times 1 minus zi divided by e of xi. Okay, and again, to be pedantic, I'm going to write ops in the subscript. Let's move this. Okay, so you can see that this is just a plugin version of the above. Okay, and we need to make one more change. I have to change the propensity score from the true propensity score to a model. Okay, so where E is an estimate of EX. Okay, and how do we do this? So just like in the outcome regression case, we have to fit the model. Okay, we can use our logistic model, which is pretty common, or we can use some more sophisticated machine learning estimators. Okay, so this is the IPW theorem. There's one more fact about propensity scores, which is really nice. Okay, and this is that I know, so I've already assumed, okay, so again, assume unconfoundedness, which is this. Okay, I'm just going to copy and paste this time. Then, in fact, the potential outcomes are independent of the treatment even if we just condition on the propensity score. Okay. So this is saying that if you assume that we have condition independence given our covariance x, we actually have condition independence if we condition on something that's a lot coarser, which is the propensity score. Okay, so this is pretty striking because x could be high dimensional, so x could have like 1,000 different features, and e of x is just a number. Okay, so just one dimension. Okay, so this is sort of saying that propensity scores are a dimension reduction technique. Okay, so they focus on the crucial aspect of your covariance that actually matters for doing causal inference. Okay, and I just want to say that the proofs of the theorem and effect are easy. Okay, so it's really easy and you can understand it. but it's just a bit tedious, and it's going to take like half an hour to do it. Okay, so I'm just going to skip it, and I'm going to let you read about this in a textbook. Okay, and so if you think back to what the calculations that we did in the previous video for the kidney stones example, this is exactly what we were doing was exactly computing this IPW estimator. Okay. Okay, so and then let me just finish up saying that. Okay, so this quantity here was what we computed for word B. Okay, this was the average outcome in word B, and this was the average outcome in word A.